Much for your very nice introduction. Upon discussion with Matti, we decided that I would talk about on this time is an application to agriculture epidemic, very terrible, as I will explain later, is due to this bacterium called Xylella fastidiosa. The work is in collaboration with a group of people both from mathematics and from schools of agriculture, environmental sciences, between Italy, Romania, and in Italy, 2 different centers. As you can see from this picture, an olive tree, which is a very important socioeconomic element, ingredient of my home region, Apulia, in southern Italy, that I will show later geographically. It provides olive oil of high quality, well known all over the world. But now, due to this epidemic, you can see that trees are completely destroyed by this bacterium for reasons I will explain. And so the losses are very, very, very high with respect to the possibility that we may do something. And then it comes up that is our contribution as scientists, not just mathematicians, but with mathematicians too, is to offer alternative practices with respect to what is being doing. So the etiological agent of this disease is olive quick decline syndrome, is due to this bacterium called Xylella fastidiosa, which is a vector-borne bacterium, as let's say malaria for human beings. So why a plant will die? Because once infected, the bacteria multiply within the xylem vessels of the plant, and then they produce a gel which occludes the xylem vessels. And so it inhibits nutrients and moisture to the plant, and then the full tree may die. The problem is well known all over the world somehow, wherever there are olives, but also many other productive plants, grapevines, almond trees, citrus plants. So it is very relevant also, for example, in North Africa and Southern Africa, where the climate affords the production of olive trees. Tunisia is a good producer of olive oil, for example. So the vector of is this this insect is the carrier. So is this vector is called Philenus spumarius, which is a xylem sap feeding specialist. So they get nutrition from the xylem of trees, but and during the juvenile, you may recognize them in the fields, in relevant fields, because you can see this foam on some plants in what generally I will call them weeds. And you may recognize because there is some bubbles of foam on these plants. And here you find the nymphs of this insect. Then it develops and becomes the insect we see here, which flies to the olive trees. So the process is then the following: that you have the acquisition by an insect vector gets the infection by feeding a plant, which can also ornamental plants in fields and weeds. Then it carries it in the foregut of the vector, so that when it will inoculate a new host, it will carry this bacteria to the new tree and new plants. And then you have the development. So you can see in this picture, this interplay between insects and insects, then the weeds, what I will call weeds, and then the olive trees. What is very bad, again, you see, people then don't do science. The European and national authorities, they are just uprooting the infected trees. And of course, they are And they think that they have also to uproot uninfected trees in the neighborhood of an infected one, which causes tremendous social and economic drawbacks. So since it was my home region, I see this event. So I proposed this group of researchers to look for alternative management strategies. So our research is to show that by means of good, predictable, reliable mathematical models, we may propose alternative control strategies that can be identified, which are less invasive than uprooting olive trees themselves. Here I come with this concept. I hope you can read it. The idea for them is the same as if in a malaria epidemic, once you identify an infected individual, you should kill this person and all of his family, which is absurd. So you have to take care of the causes of the disease. To understand the importance of olive trees in the culture of my home region, please look at this picture. This is when you enter the Bari. Bari is the capital of the region. When you enter the airport, you find this propaganda somehow. You see that the Apulia is landscape, or feels the landscape of Apulia, and they say the keyword monumental. So the olive trees are also, you have seen at the beginning, a monument for our region, not only production. But if you travel now in the area where this epidemic exploded, is a terrible disaster, even visual disaster. So we have shown that indeed is much more efficient and less social and economic impact to remove the weeds. So to look at environment, as I usually say in my own research. So the effective population, which be humans, trees, and other kinds of diseases, okay, look at the environment. So if you stop, you cut down interconnections between the sick population, the sensitive population, okay, to the susceptible population, to the environment, possibly you may stop the epidemic. The other possibility, which is also implemented, this is less dramatic. You take away all the trees, or you change the cultivar by a more resistant one. The problem is that the quality of more resistant cultivars for olive trees, okay, the oil produced by that usually is of less quality. So if you think, so one side, we don't want to eliminate all the trees because of the monumental aspect, the social aspect, but also the quality of olive oil. We want to keep the current production of olive oil. So we need to describe. It's very difficult system. So if you want to model all aspects, of these three populations, olive trees, insects, weeds, you should include also the seasonal life cycle of the insect. Their eggs are laid down in November, then they appear, the larvae, in early spring, in February, then the nymphs appear in spring, and then the insects fly during spring and summer, and they again may disappear. But if we want to take into account all this aspect would be too much complicated. So we reduce it, and here you may see what Picasso, is not me, Picasso, not Capasso, published long time ago, a picture of reduction. You see on the left up, you can see the real bull. On the right down, you can see the very schematic and reduced bull. But as you can see, You can't reduce more, otherwise you don't have a bull anymore. So you may easily recognize why this very schematic picture is still a bull. It has all the ingredients of a bull. So we have reduced our model only to these three ingredients, main ingredients, and which is on one side you have let's put that at the center you have the insect. On the right side you have the olive trees. On the left side you have the weeds, and in green you find the susceptibles, and in pink red you find infective populations. And in this picture you can see all interactions. Indeed, they are all interacting thanks to the insects. So the point is, how can we stop? We may kill the insects, but it's very difficult to use insecticides for this. You know, we know the same problem for malaria for the mosquitoes. Very difficult, but for mosquitoes, you may one of the policies is treated nets, as you know. But on olive trees, which are much larger, it's very hard to introduce treated nets. So, but we may discover that, as I will model, as I showed at the beginning, that these insects need some kind of hospitality by the weeds during the evolution, the first cycle, the first part of the life cycle. So the idea is, why don't we think of eliminating the weeds? And then this implies eliminating insects. So why not to think in these terms? So we start the dynamics of insect. As I said, let's call A the susceptibles and V the infectives. And you have the classical term of infection, okay, due to the infective insects, and sorry, I'm getting due to I have to go back to this picture. Sorry, one picture. So you see, I've called I the infective trees population, and V the infective insect population, and Q the infective weeds population. So if we go now here, you may see here that the insects are infected because they feed on the trees, and they feed on the weeds. Okay, so they become infected because of that. So you can see here, because they get information from the infected trees and from the infected weeds, and so they become infected the insects. Okay, so then we go on with the trees. Okay, the trees, vice versa, are infected because of the infective insects, and they decay, and so on. Note that here there is not a term like this, let's say saturating, because this is explained in our paper by work done by Klaus Dietz on the insects, mosquitoes for malaria. But here there is an interesting point before, that the reproduction of insects, when they start, they are all susceptibles. There is this term, which is the sum of all weeds population. So essentially, they can't reproduce without this term. If we don't have weeds where you lay down the eggs, the insect lay down the eggs and develop as larvae and nymphs, they can't reproduce. This is why this will be the key issue in our modeling. And then eventually we go here to the weeds population that follow the same kind of modeling. Everything is in our paper published in ecological modeling last year that I will refer to. So the journal is ecological modeling. So here is better to play with fractions as usual. So we introduce the fraction of susceptible insects, X the fraction of susceptible trees, and W the fraction of susceptible mass, weeds mass. If we do this, the system becomes rather complicated, but 6 equations. And here it comes up the concept, the fact that you see the total population, F, N, and M are total populations. So the insects, you see here, you have, apart from the logistic term, okay, here, you have this term M, which is the total weeds population. So that it is a clear information a priori, apart from the mathematical analysis, that we can play on this M. But the treatment is not so easy. So we have sent just now a paper to another journal in which we do analytically everything very nicely proven and so on. I will talk about that too, because what we need to do, as usual, in this kind of dynamical systems, we look for the equilibria. So we put equal to 0 all these terms, and we should solve this system to find the equilibria. So, but the equilibria, if they exist, we need to show they are attractors, and attractivity and stability is a way to prove the qualitative behavior of our system. So not only to show equilibria, but we need to show which ones are attractive and stable, so that eventually we may prove what is called global asymptotic stability, which means that any trajectory starting in the region of attraction, they go to this equilibrium. So the point is also to understand how large is the region of attraction. Would be very happy if they are global attractors, so that we have global asymptotic stability, which excludes other equilibrium under the given assumptions. And this is the program of what I'm going to show. So first of all, in the model, we have written this H1 as the cutting down of weeds, is the rate of elimination of weeds. So in the model, we go back to the picture. You see it appears here in the last equation for the total population of weeds. You can see H1. So at first we examine the system without action by the human population. But of course, how can we get a disease-free equilibrium? Well, the most trivial possibility that there is absence of contagion. So the rates of contagion rates, lambda, called lambda and eta, lambda is on live trees and eta on the weeds is 0. Then it's clear that it's easy to go back under these two assumptions to the system of the equilibria, and we get these ones. And clearly we have that when you see 1, 1, 1 here are the fractions of susceptibles, which means there is no infection. And the total populations are these 3 quantities, which are related clearly to the dynamical properties of the ecosystem in absence of the infection. So you see this part is the population, total population of insects. So they are welcome to live with this M1, which is the equilibrium C2A. Okay, so of course we need that C2A M1 should be greater than N over R. But if you go to the parameters of a real ecosystem, the reproduction rate of insect is so large, and the death rate is so small that that we that surely C2A is greater than this quantity, so it is feasible, this system. For the olive trees, L is the cutting rate, the pruning rate. They do it every year. The practice is to prune the olive trees, and in absence of infection, you just have reproduction rate of the olive trees, of the biomass of the olive trees, and the pruning rate. C is the carrying capacity depending on the environment and so on. So still without cutting, now if we are in presence of contagion, so lambda greater than 0 and data greater than 0, then we have two situations here. We may identify possibly two equilibria for the x we said is the fraction of healthy olive trees. So if this fraction goes, this is just an a priori theorem, so we don't know if this will happen. But if this is greater than this quantity, less than 1, of course, is empty, then there exists a possible feasible equilibrium, non-trivial, where all variables are present. So we may have coexistence of olive trees, insects. So they are not capable to destroy completely the olive tree population. But this we have to understand under which conditions may happen. The other possibility is that the equilibrium of the susceptible population of the olive biomass is below that level, mu plus L divided mu plus Q. Of course, L is always less than Q, so this fraction has a meaning less than 1. So if this happens, then you can see here that N3, the total population of all olive trees, goes to 0. So, but how we can a priori discriminate between X star being below or this level or up that level, so that we may understand which practice of prevention. Then we have to so you see, this is the discrimination. So we may play on the parameter of contagion of lambda of the olive trees. What is lambda? Is the resistance of the olive tree to contagion by this insect. So if the cultivar is the kind of olive tree that we produce, we cultivate, the lambda is the kind of cultivar, so the kind of olive trees. So it characterizes the resistance of the species of olive trees. And indeed, we have examined here, but this is only by some qualitative, some conjectures, but it is mathematically supported by numerical simulations, that if lambda is sufficiently small, which means strong olive trees, then we may have coexistence of infected insects and healthy olive trees. This is why the agronomists are using this practice to change the olive trees, because they don't know, they did not understand how to eliminate the infected insect. If lambda is sufficiently large, so we have the less resistant olive trees, then olive trees go extinct. So good quality olive trees are more likely to be extinct. This is unless we do more. So now we go to the equilibrium that we call A4. We cut, we make H1, the cutting rate of weeds, greater than reproduction rate of weeds, which we denote by small a. And we can show very easily analytically that if H1 is greater than A, then we have full eradication of the insects. 0 means the total insect population goes to 0, together with the total population of weeds. Is irrelevant the values of the percentages of the fractions, which anyway will stay bounded in 0, 1. So the point is we look at the total populations, insects, trees, and weeds. This is the best situation, of course, because now, independently, okay, of the cultivar, we may protect the olive trees biomass independently. So here is irrelevant the value of lambda. So we may introduce, and this is the less expensive practice, because anyway, you have to clean the orchard because of many other good reasons. We have the good practice of cleaning. What happened in the region where this epidemic exploded? Because because of the lack of maintenance, they didn't care. Because anyway, the olive trees produce olive oil, which is used only in industrial applications. Okay, this region became very famous, that part of Italy, because they were producing oil for the lamps in Europe up in the early 19th century. Okay, so because they didn't care about quality, they only needed oil for the lamps. But now they sell this oil mixed up with good quality oil for food production, which is anyway not a good quality oil, of course, less expensive. So we go to the summary. We go to the summary. We have an equilibrium A1, which corresponds to this is free, but this is only in absence of contagion. E2 is an equilibrium where we may have coexistence, but low quality oil, and E3 that we may get, we destroy the olive tree biomass is destroyed because the trees are less resistant. And then E4 is the one we like. We eradicate the insect population by the eventual eradication of the weed biomass. So you see, working on the environment, we can eradicate the disease. So of course, since in this community there are many theoretical mathematicians, they may like to see that the invariant region is found here. Then we apply Lyapunov functionals, which are not so trivial in these cases. And we show that indeed we have global asymptotical stability in the invariant region, which is the whole domain. Which means that when any of these equilibria exists, there will be the only one, will be unique. And this is a very nice theoretical result. But of course, it is important from the point of view of the agronomic practices. Okay, the parameter key is a parameter of scale. I will not discuss this much. But here we went to numerical simulations, and in presence of disease, you see when lambda is sufficiently small, okay, even though we start an epidemic, then the trees may go down for a while, but eventually they will go to a new equilibrium, okay? And so if you look, the three bottom pictures are total insect, total trees, and total weeds. And so you have eventual coexistence. But if we have a very, very high infection rate, you see the two bad parts survive and the trees disappear. So this is clearly shown how we may not like this equilibrium 3. And now, even though we have a strong infection rate, but we cut down, you see H1 is greater, even a little bit more than the production rate of weeds, even a little more. But insects and weeds don't survive, and the trees go down for a while, and then so depending on how big is the infection rate, this period of low, this is not zero, but be careful, it is written here, is not zero. And you can see that they may go up. So playing upon H1 and lambda, you will see a different period of low level of production of olives, yes. Now, if you don't have any question about this, I will show a very important extension of this, which appeared recently in the Vietnam Journal of Mathematics, on the role of the spatial structure on the Xylella epidemic. Let me introduce a concept that I've applied to my modeling papers on malaria control. You see, the idea of my own literature, in collaboration mainly with Sebastian Anitza from Romania, is that if we have the region of the habitat is this capital omega, this red pictured zone, is that necessary to intervene everywhere in order to eradicate an epidemic? It may be unfeasible, for logistic, for limited resources, and so on. So we need to invent the possibility, to think of the possibility, in this case, to treat the system, the insect population, the vector, only in a sub-region, strictly contained in capital omega. We call it small omega. So this idea of, is it possible, while thinking globally of eradicating our epidemic, to act only locally in a sub-region? Well, in our literature on malaria, we have shown this is possible. And for malaria in particular, everybody knows, for logistic reasons and also for lack of resources to give treated nets to all children all over Africa. It's very, in any habitat, it's very hard. It is written by WHO, it is written by UNICEF and so on, that are paying a lot of attention. So giving the bed nets, even though to a subset of the total population of habitat, in the habitat, we may still possibly eradicate, reduce the impact of the epidemic everywhere. And so, and this clearly may improve the ratio cost effectiveness of real control strategies. So is it possible? So this is the point. So now I emphasize mainly the total insect population and the total trees population that I denote by CI of XT and CT of XT. Though we model the evolution of the susceptible and infective. Here you can see I don't speak about weeds because we simplified further our model, otherwise the mathematics would have been crazy. So we take M of X as a given field of weeds concentration all over the habitat. Well, this means anyway that we may control via this M of X, which is not a dynamical variable in this reduced model. So what are the possible controls? Acting only in the subregion. We may put traps. Well, as I said before, this can be done for mosquitoes and malaria. It's very unfeasible for olive trees. Weed cut is possible. If we reduce the weeds population by percentage gamma to 1, then we reduce the carrying capacity of insects. We may change also cultivar by changing the infective rate the infective rate of the insect to the trees by changing the cultivar. We may reduce contacts. Well, this is less likely. It's difficult to install treated nets, even though some agronomic practices have tried to do that. They cover the tree with a net, but this can be done with small plants, possibly, not with olive trees of the size. These trees in the southern Apulia are incredibly big, incredibly big. The first picture I showed you, they are incredibly big. Also, we make clean tools because tools are used for the human practices, you know, to prune trees and so on. So this is again feasible. So I denoted with a star the practices which are unlikely, and the other one without star are practices which are likely to happen. And now the system becomes like this. These are the insects, susceptibles, and infectives. Only the insect may move around, and here we model this via random movement, so Laplace operator. And what about this term of infection? You see, I2 is the biomass of infected trees. And this is the infection rate, the contribution of the olive trees to the infection of insect at location X. This term I have always proposed also for malaria. The insects have a range of action modeled by this K, this kernel. So at point X, the insects are infected because flying around in a range of 30 meters each, let's say up to 100 meters. So they capture infection, the susceptible insect get infected because they interact in a region modeled via this K. Well, using a model that was already studied in La Peranta in the school of Mattiello by a PhD student, Sherbasheva, with Mattiario, they thought of K as a Gaussian, truncated Gaussian. So I kept this kind of information in the numerical simulation in my group. And so we left this kind of modeling so that we may use this either for malaria or whenever you have an insect around, you know, a vector, you know, then you may think, okay, of this kind of. Here are the controls. I put them in red to show that indeed you have the action only in this neighborhood, this small omega, you see? This is, so the action is, this is the characteristic function of the region small omega. So the controls, gamma 2 1 on the weeds, gamma 1 on killing possibly the insects. And here is the control upon communication between the two populations and so on. So you see, now we go to the trees and we found now the infection rate, you see, of the trees. So how can we change it? By changing cultivar, the kind of trees, and then olives, and then olive oil. And this is by cleaning the tools. L is the rate of pruning, cutting the trees. And B is the infection rate due to these practices. So again, all these red control terms are acting only, only on this subregion. So what can we say with this new model? So some small mathematics, well, not so small, but at least synthetic. So as usual, we have to play with the principal eigenvalue for this parabolic, elliptic problem. So for the parabolic equation. So this is related to the, if we go back to where it appears, it relates to this equation of the insects. Okay, you have the Laplace operator, then the weeds population, and so on. So if we go to here, you find that you have this, the change of removal rate of insects. This is the weeds population. So how this may depend upon this eigenvalue, which is very important. It's the sign of lambda 1 tilde will be crucial for stability and instability of the trivial solution of the reaction diffuser system of trees and insects. But what is interesting about this eigenvalue problem? This eigenvalue problem depends on the controls, of course, gamma 1 and gamma 2,1. I pay more attention to gamma 2,1, please, because it's the action we can really do. And then here is M, the weeds population. But here we have also dependence upon small omega, the region of intervention. Well, it's clear that this eigenvalue is an increasing function of all these parameters, gamma 1, gamma 2,1, and by small omega by inclusion. So larger the region of intervention, larger will be lambda 1, which is intuitive. And also intuitive is the fact that M plays a role. If M becomes smaller, okay, lambda 1 will become bigger, as you can see from the signs, okay? And then this shows that indeed, also for the reaction diffusion system, if lambda 1 tilde is greater than equal than 0, the total insect population will go to 0 in the space of bounded functions, upper bounded functions. So we may in particular observe that lambda 1 depends upon the field of weeds too. So altogether we may say for small values of the weed distribution or a large value of the control parameters, okay, then, which means either we cut the weeds or we change the cultivar of the olive trees, then we may really make the ecosystem hostile to the infection. To show you where we are acting, southern Italy, Apulia is like a leg. This is then the heel of this boot. And this is in red is the part where it started the epidemic. It's going on and on and on, moving like this. And here you see the map of the public authorities that they are uprooting olive trees everywhere, but also they pretend to do this in this control region, which is a little bit larger than the region affected by the disease. So, but we said, well, instead of doing this, we act on small omega, we act everywhere. We take a region, as we said, up from let's say we call this 0 and this one 250 kilometers. We act there, but only by cutting weeds, not doing anything else. And it is interesting to see that even taking, okay, a large susceptibility, large, large infectivity of the trees, we have the following. If we do an experiment, this is now our region, okay? Let's say from right, we have the tip of the boot, and here is the other part of the region, okay? So all this rectangle should represent the region, and we start from here. So the region is long about 400 kilometers, and we will control up to 250, which is here, okay? Without control, we start like this. So the infection starts here. I2 is the infected trees. We start here. And then you can see the propagation of the infection. So the number of susceptible trees decays. Here is the good ones, and here the bad ones. And the infected trees, you see, expand even more. But if we treat, we can see this is a starting situation, and we have after control, it stops. You see? So while without control, we have the expansion. I have even the movie, but it's difficult to present. With control, we start and stops, immediately stops. We have values of 10 to -4 here. So you can see how we can prevent the expansion of the disease in this way. So what we have to do now in the future? First of all, one point is that the public health, the public agronomic authorities, which are well financed by Brussels, is very strange. They did not, since they did not have a mathematical model in their hands, they did not do experiments to measure the parameters of our model. So we went by conjectures, okay? But so our simulations only show possibility, feasibility, but the figures of the parameters are still under investigation. So we hope that this induces the public authorities, and Europe first, to change practice and to finance projects of measuring parameters, which are very important in the global simulation computational experiments. So let's go another point. So once we have these numbers more and more, then we may even improve our model, because we may have more information about the ecosystem, the varieties of weeds, okay? Because also the weeds are very much affected by these insects, even ornamental weeds like lavender, rosemary, and many other kinds of weeds which are ornamental are affected by this. And the impact on the economy of our region has been terrible. Oleander, the nurse, how do you call these houses where they sell plants, nurseries, they can't sell plants. They can't sell plants from that region. All nurseries, plant nurseries, have been stopped. Can you imagine the impact? And Brussels cannot cover this in full, as for COVID. So the problem is to have a sound mathematical model, which once we have a very good mathematical model, we may really write down a cost functional and move on and go to optimal control. as we do for malaria and other kind. Optimal control, in which in the cost functional, we put all costs, positive and passive, including the quality of olive oil. They don't care. But you see, you can imagine there is a big competition, including Europe itself, because Spain, Italy, Greece are oil producers. So there is, again, well, I should not mention this in a public speech. As for COVID, there is a strong competition now among big pharmas. What is the best vaccine, as you know? But, and also where to go. When we say think globally, act locally, we have to optimize also whom has to be vaccinated. For the plants, we know we kill the weeds. But for human beings, how you decide which age interval, this is again local intervention by segmenting time on age. Which subpopulation is better to vaccinate, to eradicate faster the global epidemic of COVID? This is what we need to do. So a sound mathematical model is a must. So this presentation, I hope, may influence the way public authorities are considering controlling epidemics. Malaria, which is, for me, sorry, not because I'm talking mainly to Africans, but malaria has been killing many more people in Africa than COVID recently. But you see, this is a way to act. So now everybody is affected, and so we pay so much attention. So if I'm provoking, but World Health Organization should do optimal control strategies with sound scientific methods. And scientific methods in this case means human populations of mathematicians, agronomists, engineers, physicists, all what we need, because attacking an epidemic means environment. We need to understand where the insect live, where the insect reproduce, and so on. For malaria, we need to act on places where the mosquitoes reproduce, and so on and so on. So you see the parallels? Everywhere, any epidemic has its own structure, but we can't think that we have only one model for every epidemic. Okay, these are the papers that we have been working on this topic. And for any kind of epidemic, let me attract your attention on my book at the top, which was published first time in '93, but now I'm glad that Springer considered classic, so they wanted a reprinting in 2008. And there are many concepts about epidemic modeling that can be of use in any other situation. So thanks for your very kind attention and for the invitation.